a universe of galaxies, oceans, mountains, and living minds is built from structures so small that no eye can see them. Yet atoms were not always here. In the first moments after the Big Bang, the cosmos was too hot for even a single one to survive. Light became particles. Quarks locked themselves inside protons. Nuclei formed in a brief nuclear fire, and then the universe waited hundreds of thousands of years for electrons to finally settle into place. Only then did matter become stable enough to build stars, planets, chemistry, and life. If this quiet journey into the foundations of reality feels worth sharing, a like, a subscription, or sending the video to someone curious about the cosmos helps it travel a little farther. Thank you for spending part of your time here. What time is it where this video is playing, and where in the world is it being watched? Leave a comment below. Now, let the story of the atom begin. Across the visible universe, matter gathers into forms so different that they seem almost unrelated. A star burns with enough heat to strip electrons from atoms. A planet cools into rock, ocean, cloud, and ice. A living cell folds molecules into membranes, proteins, and strands of genetic material. Dust drifts between solar systems. Gas stretches across galaxies. Iron sinks into planetary cores. Carbon settles into soil, and hydrogen fills the spaces between stars. Yet beneath this diversity lies a quiet repetition. Nearly every familiar object is built from atoms, and every atom follows the same small set of rules. The scale changes, the arrangement changes, and the history changes, but the basic pieces remain. This is the first mystery. The universe is capable of producing black holes, coral reefs, lightning, bone, granite, and thought, but it builds nearly all ordinary matter from variations on one compact design. An atom contains a dense central nucleus surrounded by electrons. The nucleus is made from protons and, in most atoms, neutrons. Protons and neutrons are themselves made from quarks. Held together by the strong nuclear force, electrons appear to be fundamental, with no known smaller parts. From this limited inventory comes the material richness of the cosmos. The difference between hydrogen and iron is not a difference in the basic kind of reality from which they are made. It is a difference in the number of protons inside the nucleus, the number of neutrons that accompany them, and the pattern formed by electrons around them. 1 proton creates hydrogen, 2 create helium, 6 create carbon, 8 create oxygen, 26 create iron. The periodic table is therefore not a cabinet of unrelated substances. It is a map of variations on the same underlying structure. Each element is a new arrangement of familiar components, and each arrangement permits new kinds of chemistry. This repeating architecture is so common that it easily disappears into the background. Matter seems solid because atoms form stable patterns. A table resists a hand because the electrons in the table and the electrons in the hand obey quantum rules that prevent them from simply occupying the same states. Stone feels continuous, though it is mostly empty space. Air feels light, though it contains an immense number of atoms moving in every direction. The body feels singular, though it is an organized current of particles inherited from oceans, food, atmosphere, ancient stars, and the young universe itself. Atoms are everywhere, but their familiarity hides their strangeness. If an atom were enlarged until its nucleus reached the size of a small seed, its electron cloud would extend far beyond it, leaving a vast region with no hard surface and no miniature planetary tracks. The old picture of electrons circling a nucleus like moons around a planet is useful only as a first approximation. Modern quantum physics describes something less familiar. An electron does not travel along one definite orbit that can be followed at every moment. Instead, it is represented by a spread of possibilities, a pattern that gives the likelihood of finding it in one region rather than another. The atom is not a tiny mechanical solar system. It is a stable quantum structure, partly defined by what can be known and partly by what nature allows to remain uncertain. Even the nucleus is less solid than it appears. The proton is often drawn as a simple sphere, but inside it quarks and gluons form a restless system. 3 enduring quarks determine its identity, while gluons carry the strong force between them. Around these, short-lived quark and antiquark pairs appear within the shifting energy of the proton. Most of the proton's mass does not come directly from the bare masses of its 3 main quarks. It comes from the energy of the strong interaction that confines them. Matter therefore gains much of its mass not from tiny lumps packed inside other lumps, but from energy trapped in fields and motion. The ordinary world begins to look less like a collection of solid beads and more like a set of durable patterns held together by forces. This raises a deeper question. Why should those patterns exist at all atoms are not logically unavoidable? They require several conditions to be satisfied at once. There must be stable, positively charged nuclei. There must be negatively charged electrons. Electromagnetism must attract electrons toward nuclei without forcing matter into immediate collapse. Quantum rules must permit electrons to occupy stable energy states. The strong force must bind quarks into protons and neutrons, and it must also allow at least some nuclei larger than hydrogen to survive. Particle masses must fall into ranges that preserve protons, neutrons, and electrons long enough for chemistry to unfold. The universe could contain energy without atoms. It could contain particles that never bind. It could contain radiation alone, or unstable matter that decays before structure can grow. The presence of atoms is therefore not the starting assumption of cosmic history. It is an outcome. At the beginning, there are no atoms. The early universe is too hot and too dense for them. Energy fills space in the form of radiation and rapidly moving particles. Collisions are so violent that any fragile bound structure is broken apart almost as soon as it appears. Quarks cannot initially remain confined inside protons and neutrons. Later, when expansion cools the universe enough for those particles to form, atomic nuclei still cannot hold electrons. Light strikes the electrons again and again, keeping matter ionized. The first atom waits through an age in which every ingredient exists, but the final structure does not. This delay is important because it reveals that atoms are products of changing conditions. The universe must expand. Expansion must reduce temperature. The strong force must first assemble quarks into protons and neutrons. Nuclear reactions must then create the earliest nuclei. Only much later can electromagnetic attraction capture electrons into stable atomic states. Atomic matter arrives through stages, and each stage depends on the one before it. The universe does not begin with the building blocks already assembled. It manufactures the blocks from more basic ingredients, then waits until the surrounding environment becomes calm enough for them to endure. Once atoms form, they transform what the universe can become. Free electrons had scattered light repeatedly, making the early cosmos opaque. When electrons settle into atoms, space becomes transparent. Ancient radiation begins a journey that continues across the universe and remains detectable as the cosmic microwave background. Gravity then has time to gather atomic gas into larger structures. The first stars ignite. Inside them, hydrogen fuses into helium, and later generations of stars create carbon, oxygen, silicon, iron, and many heavier elements. Stellar explosions return these atoms to space. New stars and planets form from the enriched debris. Chemistry grows more varied because electron arrangements allow atoms to connect, separate, share, and exchange. Molecules appear. Some remain simple, while others become elaborate enough to store energy, form membranes, and carry information. The story of atoms becomes the story of nearly everything visible. Yet atoms are not truly everything. Most of the mass in galaxies appears to be dark matter, whose nature remains unknown and which does not seem to form ordinary atoms. The accelerated expansion of the universe is associated with dark energy, another unresolved component that is not atomic matter. Even ordinary matter can exist in forms where atoms are torn apart, as in the hot plasma inside stars. Neutron stars compress matter beyond ordinary atomic structure. Black holes hide matter behind horizons where known descriptions reach their limits. So the title of the mystery requires care. Everything familiar is not literally everything that exists. Rather, atoms dominate the ordinary material world from which planets, organisms, instruments, and observers are made. The question is therefore not why all existence is atomic, but why stable atomic matter emerges so successfully and becomes the basis of complexity. The answer begins in the first moments of cosmic history, before nuclei, before chemistry, and before light can cross space freely. It begins when energy starts producing particles, when forces separate into distinct roles, and when a cooling universe slowly moves towards structures that could not survive at the beginning. The atom appears simple only after its history has been forgotten. Seen across time, it is a late and delicate achievement, built from ancient forces, quantum rules, and a sequence of conditions narrow enough to invite wonder. The familiar world rests on that achievement. Every stone, cloud, ocean, and living cell carries the result. Beneath the forms of the universe, the same quiet architecture repeats. And behind that repetition lies a deeper story of how reality learns to hold itself together. Before atoms exist, the universe is not empty, quiet, or dark in any familiar sense. It is filled with energy so intense that matter cannot settle into lasting form. Space itself is expanding, but every region remains crowded with radiation and particles moving at nearly the speed of light. Temperature is not merely high enough to melt rock or vaporize metal. It is high enough to prevent nuclei, protons, and even some of the particles inside protons from remaining bound. The cosmos is therefore rich in ingredients but poor in structure. Almost everything collides, transforms, separates, and reforms before a stable pattern can endure. This is the first great condition in the history of atoms. Their components must appear long before atoms themselves are possible. In the earliest accessible moments, modern physics reaches a boundary. The known laws describe the universe with increasing confidence after the first tiny fraction of a second, but they do not yet provide a complete account of the beginning itself. General relativity describes gravity and the expansion of space, while quantum theory describes particles and fields. Under the extreme conditions near the beginning, both frameworks are required at once, yet they do not fit together completely. The earliest instant therefore remains uncertain. It is not necessary to imagine a small object exploding into pre-existing emptiness. The Big Bang describes an expansion of space everywhere, not an explosion from one location into a surrounding void. Every region visible today traces back to a hotter, denser state, and the distances between regions grow as space expands. The young universe is not a fireball sitting inside something larger. It is the whole observable cosmos in a radically different condition. At first, temperature is so high that familiar distinctions between particles and radiation become blurred by constant exchange. Light is made of photons, packets of electromagnetic energy. In ordinary conditions, photons travel through space and interact with matter. In the early universe, their energies are immense. Collisions between energetic photons can produce particle and antiparticle pairs. While particles and antiparticles can meet and turn back into photons, matter and radiation are not isolated categories. They move into and out of one another according to the relation between mass and energy. A particle can exist when enough energy is concentrated in the right interaction, and it can disappear when it meets its antiparticle. The cosmos becomes a restless balance of creation and destruction. Electrons appear together with positrons, their antimatter partners. Quarks appear with antiquarks, neutrinos, photons, and other particles fill the expanding space. None of this resembles a stable world of objects. It is closer to a continuously changing population of excitations in underlying fields, each interaction governed by probabilities and conservation laws. The word particle suggests a tiny bead, but quantum physics gives a less mechanical picture. Each type of particle is associated with a field extending through space. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. In the early universe, these fields carry enormous energy, and their excitations are created and erased in rapid succession. The ingredients of atoms are present, but they are not yet arranged into atoms because the surrounding environment supplies too much energy for binding to last. Binding requires a system to lose enough energy to settle into a lower, more stable state. In a cooler universe, an electron can become bound to a proton by releasing energy as light. In the young universe, the opposite happens almost immediately. Energetic photons strike any newly formed bound system and tear it apart. Even a hydrogen atom, the simplest atom, cannot survive. Its electron would be removed almost at once. Yet the obstacle begins even deeper, because protons do not form immediately either. Protons and neutrons are made from quarks, and quarks are controlled by the strong interaction. At extremely high temperature, quarks and gluons move through a dense state often called a quark-gluon plasma. They are not confined into individual protons and neutrons in the way they are later. The strong force behaves differently across distance and energy. Quarks interact weakly when extremely close together, but the force resists their separation. As the universe cools, confinement takes hold, and quarks become locked into composite particles. Before that transition, there are no stable atomic nuclei because there are no stable protons and neutrons from which to build them. Expansion drives this entire transformation. As space grows, the average energy carried by radiation decreases. The wavelengths of photons stretch, and the temperature falls. Cooling is therefore not a separate event imposed on the universe. It is a natural consequence of expansion. The young cosmos changes because its scale changes. Conditions that once made structure impossible gradually become less destructive. This cooling is continuous, but the forms of matter change in distinct stages. At one stage, quarks can no longer roam through the plasma and become confined into protons, neutrons, and other short-lived particles. At another, protons and neutrons can begin joining into light nuclei. Much later, electrons can remain attached to those nuclei. Each stage opens only when collisions become gentle enough, and the background radiation loses enough energy. Before atoms, there is also a profound imbalance without which ordinary matter would not survive. Matter and antimatter are produced together in the known interactions of the early universe. When they meet, they annihilate, returning their mass to radiation. If the amounts had been perfectly equal and every particle had found an antiparticle, nearly all matter would have vanished. Yet a small excess of matter remains. For reasons not fully understood, the early universe contains slightly more matter than antimatter. After most pairs annihilate, that tiny surplus is left behind. Every later proton, neutron, atom, planet, and living cell depends on this residue. The visible universe is built from what remains after an almost complete cancellation. The origin of this asymmetry is one of the major unsolved problems in physics. Known processes allow some differences between matter and antimatter, but they do not yet explain the observed abundance on their own. The atomic world therefore rests not only on forces that bind particles, but also on an ancient imbalance whose cause remains hidden. During these early stages, gravity plays a quieter role in the behavior of individual particles. It is vastly weaker than the other fundamental interactions at small scales. Electromagnetism governs charged particles. The strong interaction binds quarks and later helps bind nuclei. The weak interaction changes one kind of particle into another and influences the balance between protons and neutrons. Gravity shapes the expansion of the universe as a whole, but it does not assemble atoms directly. This division of a labour matters. Atoms emerge only because the forces have different strengths, ranges, and effects. The strong force acts powerfully over tiny distances. Electromagnetism reaches across much larger distances and later binds electrons to nuclei. The weak force helps determine which nuclear particles remain available. Gravity gathers atomic matter into stars and galaxies only after atoms and nuclei already exist. The universe before atoms is therefore not formless because laws are absent. It is formless because the laws operate under conditions that favour motion over binding. Structure is prevented not by chaos alone, but by a precise abundance of energy. The same forces that later hold matter together are already present, yet the environment does not permit them to create durable atoms. A proton may attract an electron, but a high-energy photon can separate them. Quarks may feel the strong interaction, but intense thermal motion keeps the plasma in a different state. Protons and neutrons may collide, but many early combinations break apart before nuclear binding can preserve them. The young cosmos contains potential structure without stable structure. This distinction gives cosmic history its direction. As expansion lowers the temperature, possibilities become realities one layer at a time. The universe first becomes capable of preserving protons and neutrons, then it becomes capable of preserving a few light nuclei. Only after a long interval does it become capable of preserving neutral atoms. The familiar solidity of matter is therefore the end of a cooling sequence, not a basic feature present from the start. Long before there are stars, planets, or chemistry, the universe must pass through an age in which nothing resembling an atom can endure. Radiation dominates the energy of space. Particles appear and disappear. Antimatter nearly erases matter. Quarks wait for confinement. Electrons remain free. The cosmos expands through this brilliant opacity, carrying within it every ingredient of the material world but none of its finished forms. The path toward atoms begins not with assembly, but with survival. Before matter can become complex, its simplest stable pieces must first find a universe cool enough to let them remain. Light fills the early universe with an intensity that makes the later darkness between stars almost impossible to recognize as part of the same history. At this stage, light is not merely something passing through matter. It is one of the main forms in which the universe carries energy, and that energy is powerful enough to become matter itself. The familiar separation between substance and radiation has not yet hardened into the categories used in ordinary life. A sufficiently energetic photon can take part in a collision that produces a particle and its antiparticle, while a particle meeting its antiparticle can disappear into new photons. The process is not a metaphorical transformation. It follows from the equivalence of mass and energy. Matter can be created when energy is concentrated in the right way, and matter can return to radiation when its mass is released. The young cosmos is therefore not stocked with a fixed supply of particles from its first moment. It is a place where particle populations rise and fall as the temperature changes. where the ingredients of atoms are repeatedly assembled from energy and erased back into light. Electrons are among the most important survivors of this age. They carry negative electric charge and later form the outer structure of atoms, but in the early universe they are born into conditions that prevent any lasting attachment to nuclei. Their antimatter partners, positrons, carry the same mass and the opposite charge. At high temperature, electrons and positrons are created freely in energetic interactions. When they encounter one another, they annihilate, producing photons. For a time, creation and annihilation nearly balance. The radiation field is energetic enough to replace many of the particles that disappear. As expansion continues, however, the temperature drops below the threshold needed to produce electron and positron pairs as readily as before. Annihilation continues, but replacement slows. Most electrons and positrons vanish into light, leaving behind the small excess of electrons required to balance the positive charge of the matter that survives. These remaining electrons will eventually enter atoms, but only after the universe has cooled for hundreds of thousands of years. Quarks follow a related but more complicated path. They are fundamental particles carrying electric charge, yet their charges come in fractions of the charge carried by a proton. Up quarks carry a positive fractional charge, while down quarks carry a negative fractional charge. A proton contains 2 up quarks and 1 down quark, giving it a net positive charge. A neutron contains 1 up quark and 2 down quarks, producing no net charge. This simple counting picture identifies the main quarks that determine each particle, but it does not capture the full activity inside a proton or neutron. Quarks interact through the strong force, and the carriers of that force are gluons, unlike photons, which carry electromagnetism but have no electric charge. Gluons themselves carry the kind of charge associated with the strong interaction. They therefore interact with one another as well as with quarks. The result is a dense and dynamic interior in which energy is constantly exchanged. In the earliest hot universe, quarks and gluons are not yet confined inside separate protons and neutrons. They occupy a state known as quark-gluon plasma, a fluid-like mixture that exists only under extreme conditions. The plasma is not simply a gas of independent beads, it is a strongly interacting medium. The early universe contains this state everywhere, not inside a laboratory chamber but across all space. As expansion cools the plasma, the strong interaction changes what can remain free. Quarks become confined into composite particles called hadrons. Protons and neutrons belong to this family. Other hadrons also appear, many of them unstable, and decay as conditions evolve. Confinement is one of the strangest features of the strong force. Pulling electrically charged particles apart usually weakens their interaction with distance. Pulling quarks apart does not release them as isolated objects. The energy stored in the strong field grows until it becomes sufficient to create new quark and antiquark pairs. Instead of extracting one free quark, the process produces new composite particles. No isolated quark has ever been observed. The building blocks inside protons are therefore permanently hidden in groups, even though their effects can be measured. When protons first become stable inhabitants of the cooling universe, the path toward atoms advances, but another balance must still be established. Protons and neutrons can transform into one another through processes governed by the weak interaction. At high temperature, these transformations happen rapidly, maintaining a shifting ratio between the two particles. Neutrons are slightly heavier than protons, so as the temperature falls, the balance begins to favor protons. Eventually the reactions become too slow to keep pace with expansion. The proportion of neutrons is effectively frozen, though free neutrons continue to decay. This surviving population matters because neutrons allow the formation of nuclei more complex than a single proton. Without them, the universe would be almost entirely hydrogen. The weak interaction therefore contributes quietly to the future periodic table by setting the supply of neutrons available when nuclear fusion begins. Neutrinos are also present in enormous numbers during this era. At first, even they collide often enough to remain part of the thermal mixture. As the universe expands and thins, they cease interacting frequently and begin travelling almost freely. A relic background of ancient neutrinos should still fill space, though it is far harder to detect than the later cosmic microwave background. Their presence is inferred from the successful description of the early universe, and from their effect on later cosmic evolution. The emergence of particle species is controlled by temperature because mass sets an energy cost. Heavy particles are easier to create when collisions carry tremendous energy. As the cosmos cools, the heaviest unstable species disappear first. They decay or annihilate, and the background radiation no longer has enough energy to replace them. Lighter particles persist longer. The universe gradually simplifies because fewer reactions remain possible. Protons remain because they appear stable over times far longer than the present age of the universe. Electrons remain because electric charge must be balanced, and because they are the lightest charged particles. Neutrinos remain because they interact so weakly. Photons remain because they are massless and stable. From this reduced population, the architecture of ordinary matter begins to emerge. Yet survival alone is not enough. The particles must also possess compatible properties. The proton's positive charge must match the magnitude of the electron's negative charge with extraordinary accuracy. If the charges didn't balance, large collections of matter would retain strong electric fields, and the behavior of planets, stars, and chemistry would be transformed. The electron must be light enough to occupy a broad atomic cloud, rather than being confined too close to the nucleus. The proton must be stable enough to persist through cosmic time. Neutrons must be slightly heavier than protons so that free neutrons decay, while bound neutrons can remain inside many nuclei. Each property becomes part of the possibility of atoms. These values are measured facts, but their deeper origin is not fully understood. The standard model of particle physics describes how known fundamental particles interact and predicts experimental results with exceptional accuracy. Yet it also contains quantities, including particle masses and interaction strengths, that must be determined from observation rather than derived from a deeper accepted theory. The existence of atoms depends on these values, even though the reason they take their particular values remains uncertain. This does not mean that the universe chooses atoms as a goal. Cosmic history has no demonstrated intention guiding it toward chemistry. Atoms emerge because particles with certain properties exist, because forces act in certain ways, and because expansion lowers the temperature through the necessary sequence of conditions. The result can appear inevitable when viewed from the present, but it is only inevitable given the laws and parameters already in place. A different set of particles or forces might produce no stable nuclei, no electrons, or no bound structures resembling atoms at all. The young universe carries no guarantee of the later world. It carries opportunities established by its physical rules: light, quarks, electrons, neutrinos, gluons, and the fundamental interactions move through an age of constant conversion. Most temporary forms disappear. A small excess of matter survives. Quarks become imprisoned inside protons and neutrons. Electrons remain free in the radiation-filled plasma. The pieces needed for atoms are now present, but they are still scattered and exposed, waiting for the next threshold in cooling. Before atoms can form, the universe must first build nuclei, and that construction can occur only during a brief interval when the temperature is neither too high nor too low. The raw material has emerged from light. The next task is to hold it together. At the center of every hydrogen atom lies a proton, a particle so familiar in diagrams that it can seem almost featureless. It is often drawn as a small positive sphere, a simple anchor for the electron cloud around it. Yet the proton is not simple. It is one of the most intricate stable structures known in physics, a compact storm of quarks, gluons, motion, and confined energy. Its radius is smaller than a trillionth of a millimeter. But within that tiny region, the strong interaction creates a world that cannot be pictured as a few solid pieces resting side by side. The proton behaves as one object from the outside, carrying one unit of positive electric charge and a definite mass, but its interior is restless. The 3 quarks used to name its basic composition are only part of the story. 2 are up quarks and 1 is a down quark. These are called valence quarks because they determine the proton's enduring identity. Their charges combine to produce the proton's positive charge. If one up quark were replaced by a down quark, the particle would become a neutron. This compact rule is accurate, but it is not a complete portrait. The quarks are bound by gluons, the carriers of the strong force. Gluons pass energy and strong charge between quarks, but unlike photons, they also interact with one another. This self-interaction makes the strong force unusually complicated. The interior of the proton is therefore not a quiet triangle linked by 3 invisible threads. It is a shifting field of exchanges where gluons multiply, disappear, and redistribute energy too quickly for any classical image to remain reliable. The strong force is described by a theory called quantum chromodynamics. The word chromodynamics refers to color charge, a property unrelated to visible color. Quarks come in 3 forms of strong charge, conventionally named red, green, and blue. These labels are bookkeeping tools, not actual colors. A stable proton combines its color charges so that the whole particle is color neutral. Just as 3 appropriately combined colors can be represented as white in the mathematical analogy, gluons carry combinations of color and anticolor, allowing them to change the color charge of quarks as they move between them. The proton remains neutral with respect to the strong interaction from the outside, while internally its charges are continually exchanged. This hidden circulation is one reason the proton is difficult to calculate from first principles. At very short distances and extremely high energies, quarks interact more weakly, a property known as asymptotic freedom. Under those conditions, they behave almost like independent particles. At larger distances inside a proton, the interaction grows stronger. The farther a quark is pulled from its partners, the more energy accumulates in the strong field between them. Eventually, the stored energy becomes large enough to create a new quark and antiquark pair. Instead of releasing a solitary quark, the process produces new bound particles. This is confinement. Quarks are real and measurable, but they do not appear alone in ordinary conditions. Their freedom exists only within the narrow interior of composite particles or in extreme states such as the quark-gluon plasma of the early universe. The proton's mass deepens the mystery. The combined resting masses of its 3 valence quarks account for only a small fraction of the proton's total mass. Most of the mass comes from the energy of the strong interaction, including the motion of quarks, the energy carried by gluons, and the ceaseless activity of the quantum fields inside. This is a direct expression of the equivalence between mass and energy. A proton is heavy not because 3 tiny objects simply add up to its measured mass, but because an enormous amount of confined energy contributes to the mass of the whole system. The ordinary weight of matter therefore comes largely from energy locked inside protons and neutrons. The mass of a stone, an ocean, or a human body is mostly not the bare mass of fundamental quarks. It is the stored energy of the strong force, repeated across an almost unimaginable number of atomic nuclei. Quantum fields also allow brief fluctuations in which gluons produce quark and antiquark pairs. These pairs are often described as C-quarks because they form a shifting background around the valence quarks. Up, down, strange, and even heavier quark types can contribute to this C, though their probabilities differ. The phrase popping in and out of existence is useful but incomplete. The fluctuations are not tiny classical particles appearing without rules. They are features of the proton's quantum state, constrained by energy, momentum, charge, and the mathematics of the field. Experiments reveal them indirectly through the way high-energy particles scatter from protons. When an electron or neutrino strikes a proton with enough energy, the pattern of the collision exposes how momentum is distributed among quarks and gluons. These measurements show that the proton's interior changes with the energy scale used to probe it. At one scale, it may appear to contain a few dominant components. At higher resolution, more gluons and C-quarks become relevant. The deeper the probe, the less the proton resembles a fixed bag of parts, and the more it resembles a layered pattern of interactions. Even its size carries uncertainty. A proton does not have a rigid edge like a grain of sand. Its radius is inferred from how electric charge is distributed and from how other particles scatter from it. Different methods once produced measurements that did not agree, creating what became known as the proton radius puzzle. Improved experiments have narrowed the disagreement, but the episode reveals how difficult it is to define the boundary of a quantum object. The proton has a measurable extent, yet that extent depends on a probability distribution rather than a hard surface. Its charge is spread through a fluctuating interior, and its apparent structure changes with the kind of question an experiment asks. The neutron is equally complex. It contains 1 up quark and 2 down quarks, giving it no net electric charge. Neutrality does not mean that charge is absent inside it. Positive and negative contributions are distributed across its interior, and the strong force binds them in the same turbulent way found in the proton. A free neutron is unstable and eventually decays into a proton, an electron, and an antineutrino through the weak interaction. Inside many atomic nuclei, however, neutrons can remain stable because the energy balance of the whole nucleus changes what decays are possible. Protons and neutrons are therefore not isolated building blocks with fixed behavior in every setting. Their stability depends partly on the structures they join. When they enter a nucleus, another layer of the strong interaction appears. Quarks remain confined inside each proton and neutron, but a residual part of the strong force reaches between neighbouring nucleons. This residual force is often compared to the faint attraction that remains outside a neutral molecule, though the underlying physics is different and much stronger. It binds protons and neutrons together over the tiny scale of the nucleus. Without it, every nucleus heavier than hydrogen would fall apart. Electromagnetic repulsion pushes positively charged protons away from one another, while the residual strong force pulls nearby protons and neutrons together. Nuclear stability emerges from the balance between these effects, along with quantum rules governing how nucleons can be arranged. The strong force is powerful, but its useful reach is short. This limited range explains why very large nuclei become unstable. As more protons are added, their electric repulsion extends across the nucleus, while the strong attraction acts mainly between close neighbours. Beyond a certain size, the balance becomes fragile, and radioactive decay becomes more likely. The periodic table is shaped by this competition. The existence of carbon, oxygen, iron, and heavier elements depends on a force that is overwhelming at tiny distances yet almost absent beyond the nucleus. Inside the proton, then, the universe hides one of its most important transformations. Energy becomes mass. Fields become durable particles. Quarks that can never be isolated combine into objects stable enough to survive for cosmic ages. Those objects later become the centers of atoms, but their apparent solidity conceals a continuous quantum motion. Every atomic nucleus carries this hidden complexity. The proton is not the simplest endpoint of matter. It is dynamic achievement of confinement, a structure held together by a force that grows stronger when its components try to escape. Before electrons can gather around nuclei and chemistry can begin, the universe must first master this deeper form of binding. The atom depends on the proton, and the proton depends on a hidden sea of interactions that never become still. The first nuclei appear during one of the briefest creative intervals in cosmic history. The universe is only seconds old, yet it has already passed through conditions that no star can reproduce across all of space. Protons and neutrons now exist as stable composite particles, their quarks confined by the strong interaction, but they're still surrounded by radiation energetic enough to destroy fragile nuclear bonds. Expansion continues to cool the cosmos, and cooling creates a narrow opportunity. If nuclear reactions begin too early, energetic photons tear the products apart. If they begin too late, particles move too slowly and remain too widely separated to collide often enough. The universe must pass through a small range of temperature in which nuclei can form and survive, and it crosses that range only once. The first step appears simple. A proton joins with a neutron to create a deuteron, the nucleus of heavy hydrogen. Yet this union cannot endure immediately. The binding energy of a deuteron is modest, and the young universe contains an enormous number of photons for every proton or neutron. Even after the average photon energy drops, the high-energy tail of the radiation still includes enough destructive photons to break deuterons apart. This delay is known as the deuterium bottleneck. Protons and neutrons are ready to combine, but their first stable bridge into larger nuclei remains vulnerable. The universe must cool further before deuterons can accumulate faster than radiation destroys them. During this waiting period, free neutrons slowly decay. A neutron outside a nucleus is not permanently stable. Through the weak interaction, it transforms into a proton, an electron, and an antineutrino. The longer nucleosynthesis is delayed, the fewer neutrons remain available for helium. The final abundance of the light elements therefore depends on a race between expansion, cooling, nuclear binding, and neutron decay. When the temperature falls enough for deuterium to survive, the bottleneck opens suddenly. Deuterons begin capturing additional protons and neutrons. Some reactions produce a nucleus containing 2 protons and 1 neutron, a form of helium called helium-3. Others produce 1 proton and 2 neutrons, a form of hydrogen called tritium. These intermediate nuclei collide and combine through several reaction paths, but many of them lead toward the same especially stable destination helium-4. Containing 2 protons and 2 neutrons. Helium-4 is tightly bound. Once its nucleus forms, it is difficult for the surrounding radiation to break apart. In a matter of minutes, a large fraction of the surviving neutrons becomes locked inside helium. The result is a universe dominated by hydrogen nuclei, with helium accounting for roughly a quarter of the ordinary matter by mass. Small traces of deuterium, helium-3, and lithium also remain. This process is called Big Bang nucleosynthesis. The first large-scale manufacture of atomic nuclei. It does not create a rich periodic table, it creates a sparse beginning. Hydrogen is overwhelmingly common. Helium is abundant but secondary. Lithium exists only in tiny quantities, and elements heavier than lithium are almost absent. The reason lies partly in time. Expansion lowers both temperature and density. Nuclear reactions require collisions, and collisions become less frequent as the universe grows. The window remains open for only a few minutes before conditions become too cool and too thin for fusion to continue efficiently. The reason also lies in nuclear structure. There are no stable nuclei containing 5 nucleons, and no stable nuclei containing 8. These gaps interrupt easy pathways toward heavier elements. Helium-4 is stable, but adding 1 proton or 1 neutron does not produce a durable nucleus with 5 particles. 2 helium-4 nuclei briefly create a system with 8 particles, but that combination is unstable and falls apart. In stars, heavier elements eventually overcome these barriers because extreme density allows 3 helium nuclei to interact through a delicate sequence, producing carbon. The early universe expands too rapidly for that process to proceed on a meaningful scale. Its first nuclear furnace is everywhere, but it burns for too little time. The universe therefore leaves its opening act with nuclei but almost no atoms, and with only the lightest elements available. The abundances produced in these first minutes become one of the most important tests of the hot Big Bang model. The calculations begin with measured nuclear reaction rates, the expansion history, and the number of ordinary particles compared with photons. From these ingredients, physicists predict how much hydrogen, helium, deuterium, and lithium should remain. Astronomers then compare those predictions with ancient gas clouds, old stars, and other environments that preserve material with little later processing. The broad agreement is remarkable. The amount of helium matches a universe that once passed through a hot, dense nuclear phase. Deuterium is especially useful because stars tend to destroy it rather than create large new supplies. Its surviving abundance acts as a sensitive record of the density of ordinary matter in the young cosmos. Yet the agreement is not perfect. Measurements of primordial lithium remain lower than standard calculations predict. This mismatch, often called the cosmological lithium problem, may reflect uncertainties in stellar evolution, nuclear reactions, observations, or physics not yet recognized. The first nuclei therefore provide both confirmation and an unresolved detail. They show that the early universe follows a calculable thermal history, while leaving a small but persistent sign that the account may still be incomplete. The formation of nuclei also reveals why ordinary matter does not become a featureless sea of protons. The neutron, though unstable in isolation, can survive when bound inside a stable nucleus. Nuclear binding changes the energy balance of decay. In helium-4, the arrangement of 2 protons and 2 neutrons is so tightly bound that the neutrons endure. This allows neutral nuclear matter to become part of long-lived elements. Neutrons reduce the electric strain within nuclei because they contribute strong attraction without adding positive charge. As nuclei grow heavier in later stars, increasing numbers of neutrons help offset the repulsion among protons. The architecture of the periodic table begins with this partnership between charged and uncharged nucleons. Still, the partnership is constrained. The strong interaction attracts nucleons only across extremely short distances, while electromagnetism pushes every proton away from every other proton across the nucleus. In the smallest nuclei, the strong force easily wins. In larger nuclei, the balance grows more complicated. Quantum rules determine which energy states protons and neutrons can occupy, and certain combinations become especially stable. None of this complexity is fully expressed during the first minutes because the universe lacks time to construct heavy nuclei. Yet the principles are already present, waiting for stars to use them later. Big Bang nucleosynthesis also fixes the initial chemical simplicity of the cosmos. There is no oxygen for water, no carbon for organic molecules, no silicon for rock, and no iron for planetary cores. The first nuclei can support only a universe of hydrogen and helium gas with faint traces of lithium. Complexity must wait for gravity to gather this gas into stars, Those stars will create new nuclei through fusion, and their deaths will scatter enriched material into space. The first nuclear era does not build planets or life. It establishes the raw fuel from which all later stellar chemistry grows. Hydrogen becomes the most abundant element because the conditions favour isolated protons after the brief fusion period ends. This abundance shapes nearly every later stage of cosmic evolution. Hydrogen gas collapses into the first stars. Hydrogen fusion powers them. The light released by stars changes surrounding gas and eventually helps ionize the universe. Hydrogen later enters water, hydrocarbons, and biological molecules. Its dominance is not an arbitrary feature of the modern cosmos. It is a fossil of the narrow nuclear window in the first minutes. Helium carries the same ancient signature. Much of the helium in the universe is older than every star. Stars produce additional helium, but a large primordial supply exists before the first stellar core ignites. The ratio between hydrogen and helium is therefore a surviving memory of conditions when the universe is younger than an ordinary human conversation. By the time nuclear reactions cease, cosmic history has taken another decisive step toward atoms. Stable nuclei now exist in abundance. Positive charge is concentrated into protons and helium nuclei. Electrons remain free, moving through a hot plasma and scattering photons. The ingredients are no longer merely fundamental particles. They have become durable nuclear structures capable of lasting across billions of years. Yet they are still not atoms. The surrounding radiation remains too energetic, and any electron captured by a nucleus is quickly knocked free. The universe must expand by an immense factor and cool for hundreds of thousands of years before electromagnetic binding can complete what the strong force has begun. The first nuclei therefore mark both an achievement and a pause. Matter has learned to bind at its deepest ordinary level, but the outer architecture of atoms still waits beyond a long age of light. After the first few minutes, the universe enters a long waiting period. The main light nuclei have formed, but atoms have not. Hydrogen nuclei are simply protons. Helium nuclei hold 2 protons and 2 neutrons, and a faint trace of deuterium and lithium survives from the brief era of primordial fusion. Around them moves a population of free electrons. Every ingredient needed for atoms is present, yet the environment remains too energetic for those ingredients to stay together. The universe is no longer hot enough to build many new nuclei, but it is still far too hot for electrons to settle into stable atomic states. This creates an immense interval between nuclear creation and atomic creation, a span of hundreds of thousands of years during which matter remains a glowing plasma. A plasma is a gas in which electrons are separated from nuclei. Because the particles carry electric charge, they respond strongly to electromagnetic fields and collide continually with photons. The young cosmos is therefore not transparent. Light cannot travel far before striking a free electron and changing direction. Photons scatter through the plasma again and again, following tangled paths rather than crossing space in straight lines. No distant object could be seen through such an environment, even if stars had somehow existed. The universe resembles a dense luminous fog, though the fog is made not from droplets, but from charged particles and radiation in constant interaction. This opacity is central to the delay. A proton and an electron attract one another because their charges are opposite. In cooler conditions, that attraction allows the electron to enter a bound quantum state around the proton, creating hydrogen, yet binding releases energy, and the new atom can survive only if the surrounding photons are too weak to reverse the process. In the early plasma, enough photons carry energies above the ionization threshold of hydrogen. Whenever an electron is captured, another photon soon arrives and knocks it free. The attraction works, But the background radiation undoes its work. The universe must cool until destructive photons become sufficiently rare. This takes far longer than a simple comparison with the average temperature might suggest. There are enormously more photons than atomic nuclei, so even when only a small fraction of photons remains energetic enough to ionize hydrogen, that small fraction can still outnumber the atoms. The plasma therefore stays ionized until the average photon energy falls well below the energy needed to break a hydrogen atom apart. The delay is another bottleneck, similar in spirit to the earlier deuterium bottleneck. In both cases, a bound structure becomes possible before it becomes common. The universe must cool beyond the obvious threshold, because the high-energy tail of the radiation continues to destroy what is formed. Expansion patiently weakens that radiation as space grows. Photon wavelengths stretch and their energies decline. The cosmic temperature falls from the fierce heat of nucleosynthesis toward a few thousand degrees. Matter also becomes more dilute. Protons, helium nuclei, electrons, and photons occupy an increasing volume, and collisions happen less often. During the first part of this long period, radiation dominates the energy density of the universe. Photons are so abundant and energetic that they influence the expansion more strongly than matter does. Later, as their wavelengths continue to stretch, radiation loses energy faster than matter. A transition occurs when matter becomes the dominant component among matter and radiation. This change allows gravity to begin strengthening small variations in density more effectively. Slightly denser regions attract additional matter, while slightly emptier regions lose it. The beginnings of future structure are present. But ordinary matter cannot collapse freely because it remains tightly coupled to radiation. Photons push against electrons, and electrons interact electrically with nuclei, so the whole plasma behaves as a linked fluid. Gravity tries to compress denser regions, while radiation pressure pushes outward. The result is a pattern of waves moving through the primordial plasma. These are often called baryon acoustic oscillations. Baryons are particles such as protons and neutrons, and acoustic refers to pressure waves. They are sometimes described as sound waves because compression and rarefaction travel through matter, though their scale and frequency are far beyond familiar sound. The waves move outward from early density variations, carrying ordinary matter and radiation together. Their motion leaves a measurable imprint on the later distribution of galaxies, even during the age before atoms. The universe is already preparing the large-scale pattern into which stars and galaxies will eventually settle. Dark matter behaves differently. It does not appear to scatter light or carry electric charge, so radiation does not hold it in the same way. Dark matter can begin gathering gravitationally into denser regions, while ordinary matter remains trapped in the photon-driven plasma. These early concentrations form gravitational wells. After atoms finally appear and radiation releases its grip, ordinary gas can fall more freely into those wells. The long wait for electrons therefore shapes not only atomic physics, but cosmic architecture. The timing of atomic formation determines when ordinary matter can separate dynamically from light and begin joining the structures already outlined by dark matter. During this interval, helium begins capturing electrons before hydrogen does because its greater nuclear charge binds them more strongly. The sequence is not a single instant in which every atom appears at once. Helium nuclei first acquire one electron and later a second as the temperature falls through the relevant ranges. Hydrogen follows when protons can keep electrons bound for long periods. Even then, the process is not perfectly direct. An electron captured into the lowest energy state of hydrogen would need to release a photon energetic enough to ionize another nearby atom. This can simply pass the problem onward. Captures into excited states, followed by carefully permitted transitions, help the universe escape this cycle One especially important pathway involves a rare transition from a metastable state in which the electron releases 2 photons rather than 1. Another depends on photons associated with a particular hydrogen transition gradually escaping through the expansion of space. These details slow atomic formation. What appears in a simple diagram as an electron falling into place is, across the real universe, a network of quantum transitions, repeated absorption, photon escape, and cosmic expansion. The word recombination is traditionally used for this era, although the prefix suggests that electrons and nuclei had previously been combined. In the standard hot Big Bang history, they're combining into neutral atoms for the first time. The name survives from earlier cosmological ideas and from the language of plasma physics. Whatever the label, the transformation is decisive. Before it, free electrons scatter light efficiently. After it, most electrons are hidden inside neutral atoms, and photons encounter far fewer charged targets. Matter does not become completely neutral in every location, and a small fraction of free electrons remains, but the opacity drops dramatically. The universe changes from a glowing fog into transparent space. This transparency does not mean darkness disappears. The released radiation fills the cosmos, and at the moment of departure it carries a warm visible and infrared glow. Yet there are still no stars. After the light decouples from matter, the universe enters the cosmic dark ages. The ancient glow stretches to longer wavelengths as space expands. While no new visible sources have yet ignited, atomic hydrogen and helium drift through a growing universe, cooling and collecting slowly under gravity. The first atoms are therefore born into a period that is both transparent and starless. Their arrival opens space to light, but the next great sources of light must wait for gas to collapse into the first stellar cores. The long delay before atoms also reveals a broader principle. Stable structures depend not only on the existence of attractive forces, but on the energy of their surroundings. Electromagnetism is present from the earliest eras. Protons and electrons attract throughout the plasma age, yet attraction alone cannot guarantee binding. The background can supply enough energy to tear systems apart faster than they form. Stability emerges only when the environment falls below a critical level of disturbance. The same idea appears throughout nature. Molecules dissociate when heated, solids melt, nuclei break apart under sufficiently energetic collisions. Structure is always a balance between binding and disruption. In the early universe, expansion steadily shifts that balance toward order. For hundreds of thousands of years, the final step toward atoms remains just beyond reach. Nuclei endure, electrons roam, and photons strike them without rest. Then the radiation cools. Quantum pathways begin to preserve captured electrons, and the plasma loosens its hold on light. The universe has waited far longer for this transition than for all the nuclear reactions of its first minutes. When it arrives, the change is rapid on a cosmic scale. Free charges vanish into neutral structures, opacity collapses, and the oldest light begins its uninterrupted journey. The atom is almost complete, and with it the visible universe is about to become transparent for the first time. The birth of atoms does not occur as a single flash, but across a narrowing interval in which the universe finally becomes cool enough for electric attraction to survive the surrounding sea of light. For hundreds of thousands of years, protons, helium nuclei, electrons, and photons move together as a hot plasma. Every charged particle feels the pressure of radiation. Every photon changes direction again and again as it strikes a free electron. Then expansion lowers the temperature to a few thousand degrees, and the balance begins to shift. Electrons still move quickly, but not quickly enough to escape every encounter with a nucleus. Photons remain abundant, but fewer of them carry the energy needed to tear a newly formed atom apart. The universe approaches a threshold at which binding stops being temporary and becomes the normal state of ordinary matter. Hydrogen provides the simplest case. Its nucleus is a single proton, carrying one positive electric charge. An electron carries an equal negative charge, so electromagnetism draws the two together. Yet the electron does not spiral downward like a small planet losing altitude. Quantum mechanics permits only certain bound states, each with a definite energy. The electron becomes described by an orbital, a stable pattern of probability surrounding the proton. To enter that pattern, the system must release energy, usually through photons. Once the electron reaches a sufficiently low energy state, the proton and electron form a neutral hydrogen atom. The word neutral does not mean that electric charge has vanished. The positive and negative charges remain, but they balance when viewed from a distance. This balance changes the way matter interacts with light. A free electron can scatter a broad range of photons, but an electron bound inside an atom can absorb only particular energies associated with permitted transitions. Most photons can now pass without encountering an effective obstacle. The road to neutrality is not perfectly direct. If an electron falls straight into the lowest energy state of hydrogen, it releases a photon energetic enough to ionize another hydrogen atom. The universe then trades one neutral atom for another without reducing the overall number of free electrons. Progress requires routes that prevent each capture from immediately undoing a previous one. Electrons often enter excited states first and then descend in steps. Some transitions release photons that are repeatedly absorbed and emitted by other atoms, trapping the radiation for a time. Cosmic expansion gradually stretches these photons to slightly lower energies, allowing them to escape the exact range that hydrogen can absorb. A rare two-photon transition also provides a path from a long-lived excited state to the ground state without producing a single strongly ionizing photon. Through these delicate quantum channels, neutral hydrogen steadily accumulates. Helium follows a related sequence, though its stronger nuclear charge changes the timing. A helium nucleus contains two protons and usually two neutrons. It first captures one electron, becoming singly ionized helium, and later captures a second to become neutral. Much of this occurs before hydrogen recombination because helium holds its electrons more tightly. Different atomic species respond to different binding energies, and even within one species the fraction of neutral atoms changes gradually. Still, on the scale of cosmic history, the transition is swift. A universe that remains opaque for hundreds of thousands of years becomes largely transparent over a comparatively short interval. The disappearing free electrons are the key. Before recombination, photons scatter through the plasma so often that matter and radiation behave almost as one fluid. Compression waves move through them, shaped by gravity and radiation pressure. After recombination, most electrons are locked inside atoms, and the scattering rate drops sharply. Photons cease exchanging energy and momentum with ordinary matter at the former rate. They decouple, which means that they begin travelling almost freely through expanding space. The surface from which this ancient light appears to depart is called the surface of last scattering. It is not a solid shell surrounding one special point. Every observer, wherever located, sees a distant spherical boundary defined by the places from which photons have had enough time to arrive since the universe became transparent. Beyond that boundary lies an earlier era hidden by opacity. The light released at last scattering carries a picture of the universe at the end of its plasma age. It begins as a warm glow with a temperature of several thousand degrees, bright enough that its spectrum lies mainly in visible and infrared wavelengths. Space is filled with this glow in every direction. There are no stars yet, so the radiation is not starlight. It is the fading thermal light of the young universe itself. As expansion continues, the wavelengths stretch. Visible light slides into infrared, then into microwaves. Billions of years later, the radiation becomes the cosmic microwave background, cold and faint but still present throughout space. Its near-perfect thermal spectrum reveals that matter and radiation were once held in close equilibrium. Its tiny temperature variations preserve differences in density from which galaxies later grow. The formation of atoms therefore leaves a direct observational record. Atomic birth is not merely inferred from theory. Its release of light remains measurable across the sky. Recombination also changes the motion of ordinary matter. Before electrons become bound, radiation pressure resists gravitational collapse. Photons push on electrons pull on nuclei, and the plasma remains coupled to light. After decoupling, neutral gas no longer feels the same pressure. It can begin falling more freely into gravitational wells, especially those already formed by dark matter. Hydrogen and helium gather slowly into denser regions. The small variations visible in the ancient radiation become the starting pattern for a cosmic web of clusters, filaments, and voids. Atoms do not create gravity, but their formation releases ordinary matter from a powerful drag. The universe becomes capable of concentrating gas into the clouds that will eventually ignite the first stars. The transition also marks the beginning of the cosmic dark ages. Transparency arrives, yet new light sources do not. The background glow continues to cool and shift beyond visible wavelengths. Neutral hydrogen fills much of space, waiting in darkness while gravity gathers matter. This period lasts until the earlier stars and galaxies form. Their radiation later ionizes much of the hydrogen again during an era called reionization. The first atoms are therefore not the final electrical state of cosmic gas. They emerge, endure through darkness, and are later broken apart across large regions by the first generations of stars. Even today, most visible matter in stars exists as plasma rather than neutral atoms. Atomic form is common, but it is not permanent under every condition. What makes recombination decisive is not that every particle remains atomic forever, but that stable atoms become possible and widespread for the first time. Their appearance opens the path to chemistry. A bare proton has electric charge and nuclear identity, but a hydrogen atom has an electron structure capable of interacting with other atoms in selective ways. Helium becomes largely unreactive because its outer electron state is complete. Later elements will display more varied electron arrangements, allowing bonds of different strengths and geometries. None of that complexity exists at recombination because almost all nuclei are hydrogen or helium. Yet the principle is established. Electrons can occupy stable shells. Atoms can absorb and emit characteristic wavelengths. Neutral matter can cool by releasing radiation. Gas can form molecules once suitable collisions occur. The first simple molecules arise through fragile combinations involving hydrogen and helium, though complex chemistry must wait for heavier elements forged in stars. The birth of atoms is therefore the moment when the universe gains a new language of structure. Before it, charged particles interact broadly through a luminous plasma. After it, electrons occupy quantized states. Light carries distinct spectral signatures, and matter begins to possess chemical identity. Hydrogen is no longer merely a proton accompanied somewhere by an electron. It becomes a coherent quantum system whose behavior differs from the sum of two isolated particles. The atom is a new whole, created not by adding extra substance but by allowing existing particles to enter a stable relation. This is why cooling matters so deeply. The laws and particles already exist, but a new level of reality appears only when the environment permits binding. As the last scattering photons begin their long journey, the universe crosses an invisible boundary. It changes from opaque plasma to transparent gas, from free charges to neutral atoms, from repeated scattering to light crossing immense distances. The transformation is quiet and almost uniform, yet its consequences extend through every later age. Without it, radiation continues to restrain ordinary matter. Stars do not form in the same way, and chemistry never receives its basic units. With it, the cosmos becomes transparent enough to reveal its earlier surviving image and structured enough to begin building everything that follows. The oldest light in the universe does not arrive from a star, a galaxy, or any object that still exists in recognizable form. It comes from a moment when the cosmos itself becomes transparent. For hundreds of thousands of years, photons remain trapped in a dense plasma, scattered repeatedly by free electrons and unable to travel far in any one direction. When electrons settle into atoms, that barrier collapses. Light begins to move almost freely, carrying with it a record of the conditions at the end of the plasma age. Across billions of years, expansion stretches its wavelengths until the original warm glow becomes microwave radiation. Today this relic fills all of space. It is called the cosmic microwave background, and it is the oldest electromagnetic signal that can be observed directly. Earlier light exists in principle, but the universe before recombination is opaque, so no photon from those times can reach the present without having been scattered. The microwave background therefore forms a natural horizon in visible history, a luminous boundary beyond which ordinary telescopes cannot see. The radiation appears almost perfectly uniform. Its temperature is nearly the same in every direction, only a few degrees above absolute zero. This near uniformity reveals that the young universe is remarkably smooth on large scales. Matter and radiation are distributed with only tiny differences from place to place. Yet perfect smoothness would have produced a very different cosmos. If density had been exactly equal everywhere, gravity would have had no preferred regions to amplify. Matter would have remained spread almost evenly, and galaxies might never have formed. The microwave background contains the small departures from uniformity that make later structure possible. Its temperature varies by only tiny fractions, but those variations correspond to slight differences in density, motion, and gravitational environment. Warmer and cooler patches do not represent stars or empty holes. They are the faint imprint of regions where the primordial plasma is compressed, rarefied, moving, or resting at different depths in the early gravitational landscape. These subtle patterns become the seeds of the cosmic web. Gravity acts slowly but persistently. A region containing slightly more matter pulls in additional matter. As it grows denser, its attraction strengthens. A region containing slightly less matter loses material to its surroundings and becomes emptier. Over immense spans of time, tiny initial contrasts become enormous structures. Dense regions grow into galaxies, groups, clusters, and long filaments. Sparse regions become vast voids. The modern universe, with its islands of light separated by dark expanses, begins as almost invisible variations in an otherwise even glow. The microwave background allows cosmologists to trace this transformation backward. It shows that cosmic structure does not appear from a perfectly featureless state, nor does it require large irregularities at the beginning. Extremely small differences are enough when gravity is given billions of years. The pattern is shaped before atoms form by waves moving through the coupled plasma of matter and radiation. Gravity draws material inward toward overdense regions, while radiation pressure pushes outward. The result is a repeated cycle of compression and release, similar in principle to sound moving through a fluid. These baryon acoustic oscillations leave a series of characteristic scales in the microwave background. Some regions reach maximum compression at the moment light decouples. Others are caught during expansion or at different phases of the wave. The sky therefore contains a statistical pattern of hot and cold spots rather than a random scatter. By measuring the strength of variations at different angular scales, physicists recover information about the contents and geometry of the universe. The pattern reveals how much ordinary matter exists, how much dark matter is present, and how the expansion behaves. It also shows that space is very close to geometrically flat on the largest observable scales. The exact later fate of each small region is complicated by motion and nonlinear growth. Instead, the full distribution is compared with predictions from cosmological models. The agreement is one of the strongest pieces of evidence that the universe passes through a hot, dense early state. The spectrum of the radiation provides a separate and equally powerful clue. A system in thermal equilibrium produces a distinctive distribution of light known as a blackbody spectrum. The cosmic microwave background follows this form with extraordinary precision. Such a spectrum is difficult to produce through ordinary stars, dust, or scattered galactic light across the entire sky. It is naturally explained if matter and radiation once interact so frequently that they share a common temperature. Recombination then releases the photons, preserving the thermal pattern, while expansion cools it. The spectrum remains the same shape even as every wavelength stretches. Only the temperature associated with the curve falls. The present microwave background is therefore not cold because it begins cold. It is cold because space has expanded enormously since the light last scattered from matter. The radiation also carries polarization, a directional property produced when photons scatter in an uneven environment. Patterns in this polarization provide additional information about motion in the primordial plasma and about later events that affect the radiation. When the first stars and galaxies produce enough energetic light to ionize much of the neutral hydrogen, newly freed electrons scatter a small fraction of the background photons again. This later ionization leaves a broad signature in the polarization. Other patterns may contain traces of gravitational waves generated in the very early universe, though separating such a signal from dust and other foregrounds is extremely difficult. It is a layered record, altered slightly by the structures and ionized gas through which it travels. Reaching that record requires careful removal of nearer sources. The sky also contains microwave emission from the Milky Way, from distant galaxies, from energetic electrons, and from dust grains. Instruments observing the background measure several frequencies so these foregrounds can be distinguished by their different spectral behavior. Space missions map the sky from above the atmosphere, where terrestrial interference is reduced. Each generation of observation improves sensitivity and resolution, revealing finer variations while testing whether the same cosmological picture remains consistent. The result is not a photograph in the ordinary sense. Colours in maps of the microwave background are assigned to temperature differences far too small for human eyes to detect, and the spherical sky is often flattened into an oval projection. Yet beneath the visual conventions lies real radiation arriving from every direction, each photon carrying energy shaped by the state of the universe when atoms first become common. The microwave background also marks a separation between what can be seen directly and what must be inferred through other messengers. Photons from before recombination are repeatedly scattered and lose any straight path from their source. Neutrinos, which interact far more weakly, decouple much earlier and should preserve information from the first seconds. Gravitational waves may travel from even earlier processes. Detecting those backgrounds would extend observation deeper into cosmic history. But the microwave background remains the clearest ancient signal currently available. It serves as a bridge between particle physics and astronomy, connecting conditions in the young plasma to the placement of galaxies across the modern sky. It also preserves evidence that atoms do more than create chemistry. Their formation changes the visibility of the universe. Before neutral atoms become widespread, light cannot carry an image across space. Afterward, photons begin to preserve location and direction over cosmic distances. The first atoms therefore create the first transparent archive. Every observation of the microwave background is an act of reading that archive, not because the atoms themselves remain in the same places, but because their appearance releases the light that records the surrounding conditions. The atoms later gather into clouds, enter stars, become ionized again, and join galaxies. The photons continue onward, stretched and cooled but still carrying the imprint of that transition. Their pattern shows that the universe is neither perfectly ordered nor violently irregular at its visible beginning. It is smooth enough to appear almost uniform, yet uneven enough to grow complexity. The balance is delicate. Too little variation would leave matter diffuse. Too much could produce an early universe dominated by collapsed structures. The observed level allows a long, gradual growth from faint density contrast to the cosmic web. In this way, the oldest light answers part of the question of why atoms matter. Atoms are not merely small containers from which larger objects are built. Their formation unlocks a new phase of cosmic evolution. It frees radiation, releases ordinary matter from pressure, and leaves a map of the seeds from which structure develops. The microwave background remains around every galaxy and every observer, an ancient glow passing silently through the present. It is the fading light of a universe newly filled with atoms, and within its tiny variations lies the outline of nearly everything that comes after. At first glance, an atom appears to contain the ingredients of its own destruction. A positively charged nucleus sits at the centre, while negatively charged electrons surround it. Opposite charges attract. So classical intuition suggests that every electron should be pulled inward. If the electron were a tiny charged planet circling the nucleus, it would also radiate energy as it accelerated along its curved path. Losing energy would make the orbit shrink. The electron would spiral downward, collide with the nucleus, and erase the atom almost instantly. Yet atoms do not collapse. Hydrogen can survive across cosmic time. Carbon can remain locked inside rock for billions of years. Oxygen can drift through interstellar clouds, enter a planet, join a molecule, leave it again, and still preserve its atomic identity. The stability of matter therefore depends on a rule that ordinary mechanical pictures cannot explain. That rule comes from quantum physics, where particles are not assigned exact paths in the same way as planets or projectiles. An electron bound to a nucleus is described by a wave function, a mathematical object that encodes the possible results of measurements. The wave function does not identify a hidden orbit waiting to be discovered. It gives a spread of probabilities, showing where the electron is more or less likely to be found. This spread forms an orbital, a stable pattern extending through space around the nucleus. The electron is not a blurred bead moving too quickly to follow. The blur is part of the state itself. In the lowest energy state of hydrogen, the probability is greatest near the proton and decreases with distance. But it does not shrink to a single point. The electron occupies a quantum structure whose size is set by the balance between electromagnetic attraction and the rules governing confinement. The nucleus pulls the electron inward, lowering electrical potential energy. But forcing the electron into an ever smaller region increases the uncertainty in its momentum. This relationship is expressed by the uncertainty principle. It does not arise from imperfect instruments. It is a basic feature of quantum states. A particle confined tightly in position must possess a wider range of possible momenta. greater momentum uncertainty corresponds to greater kinetic energy. As the electron is squeezed closer to the nucleus, the energy associated with its confinement rises sharply. Electromagnetic attraction favors a compact atom, while quantum confinement resists unlimited compression. The lowest energy state appears where these tendencies balance. That state is not motionless in the classical sense, but neither is it an orbit that steadily loses energy. It is stationary, meaning that its probability pattern does not change with time except for an unobservable phase. Because the electron is already in the lowest permitted energy state, there is no lower state into which it can fall. Collapse is prevented not by a hidden support or a miniature force pushing outward, but by the structure of the allowed quantum states. Energy inside an atom is quantized. The electron can occupy only certain states, each associated with a definite energy. Between those states there is no continuous ladder of permitted orbits. When an atom absorbs the right amount of energy, an electron can move into a higher state. When it returns to a lower state, the energy difference is released, often as a photon. The photon carries a precise frequency related to that difference. This produces the spectral lines that identify elements across laboratories and distant stars. Hydrogen emits one pattern, helium another, and iron a much richer set. The stability of atoms and the colours of their light therefore emerge from the same principle. Electrons occupy discrete quantum states rather than arbitrary classical paths. The simplest hydrogen atom can be described with remarkable accuracy, but atoms with many electrons become more complicated. Each electron feels the attraction of the nucleus and the repulsion of every other electron. Their wave functions must combine into a single many-particle quantum state. Electrons also belong to a class of particles called fermions, which obey the Pauli exclusion principle. No two identical electrons in an atom can occupy exactly the same quantum state. This restriction forces electrons to arrange themselves in layers of increasing energy. These layers are commonly called shells, though they are not hard surfaces nested like hollow spheres. They're groups of orbitals with characteristic shapes, energies, and capacities. Some orbitals are roughly spherical, others form lobes, rings, and more intricate probability patterns. The arrangement of electrons across these states determines how an atom interacts with other atoms. The exclusion principle therefore helps stabilize not only individual atoms, but the architecture of the periodic table. As protons are added to the nucleus, electrons fill the available states according to quantum rules. Atoms with similar outer electron arrangements display similar chemical behavior. Elements in one column of the periodic table tend to form related bonds because their outermost electrons occupy comparable patterns. Noble gases are unusually unreactive because their outer shells are filled. Alkali metals readily lose an outer electron. Halogens tend to gain one. Chemistry is built from these tendencies, and those tendencies begin with the quantum stability of electron states. Matter also resists compression because electron states cannot all be forced into the same configuration. When atoms are brought close together, their electron clouds overlap. Electromagnetic repulsion contributes to the resistance, but the exclusion principle is equally important. Electrons must rearrange into different states, often requiring additional energy. This creates the stiffness of ordinary matter. A floor supports weight, a stone keeps its shape, and the atoms in a solid do not simply pass through one another because quantum rules restrict how their electrons can be combined. The apparent solidity of the world is therefore not produced by tightly packed miniature balls. Atoms contain large regions with no classical material surface, yet their quantum states create powerful resistance to overlap. The nucleus presents another apparent danger. In many atoms, electrons have some probability of being found extremely close to it. Certain orbitals even have non-zero probability density at the nucleus. Yet this does not mean the electron is swallowed. A proton and an electron can combine through the weak interaction under some conditions, producing a neutron and a neutrino in a process called electron capture. This occurs in particular unstable nuclei when the energy balance allows it. In ordinary hydrogen, however, the mass and energy of the initial state do not permit spontaneous conversion into a neutron. A neutron is heavier than a proton and electron together, so additional energy would be required. Conservation laws and particle masses protect hydrogen from this route of collapse. Atomic stability therefore depends on more than quantum orbitals alone. It also depends on the relative masses of the electron, proton, and neutron, and on the interactions that can transform them. Even a stable atom is not perfectly isolated from change. An excited electron can emit light and descend to a lower state. A high-energy photon can remove it, ionizing the atom. Collisions can rearrange electron configurations. Some nuclei decay, turning one element into another. Under extreme pressure, atoms can be stripped apart or forced into unfamiliar forms of matter. Stability means that a state persists unless a permitted interaction supplies a path to something lower in energy. It does not mean eternal immobility. Quantum systems are dynamic, but their dynamics are constrained. The ground state of a stable atom remains because no allowed process can reduce its energy while preserving all necessary laws. This quiet endurance is one of the foundations of cosmic complexity. Without stable electron states, there are no durable elements, no repeatable spectra, and no chemistry. Without the exclusion principle, electrons crowd into the lowest state. Periodic structure disappears, and matter loses much of its volume and resistance. Without the measured balance of charges and masses, protons and electrons may not form long-lived neutral systems. The atom exists because several quantum principles work together. Electromagnetic attraction binds. Uncertainty prevents unlimited localization. Quantization creates a lower state. Exclusion organizes many electrons, and conservation laws restrict destructive transformations. The result is neither a tiny solar system nor a static shell. It is a standing pattern in fields, stable, because the universe permits only certain ways for energy and probability to be arranged. Every ordinary object inherits this hidden order. Its atoms remain open, mostly empty, and ceaselessly quantum, yet they endure with enough reliability to build worlds. Once atoms become stable, the universe gains more than durable pieces of matter. It gains the possibility of relationship. An isolated atom carries a particular number of protons in its nucleus and a corresponding arrangement of electrons around it. That arrangement determines how the atom can approach another atom, how strongly the two may attract, and whether they can share, exchange, or redistribute electrons. Chemistry begins in these interactions. It is not a separate force added to physics, but the varied behavior that emerges when quantum rules act across many atoms at once. The nucleus gives each element its identity, while the outer electrons determine much of its chemical character. Because electrons occupy quantized states, atoms cannot combine in arbitrary ways. They form bonds with preferred energies, distances, and geometries. These restrictions create order, yet the number of possible combinations becomes immense. A small set of atomic rules opens a landscape of molecules, crystals, gases, liquids, minerals, and biological structures. The simplest bond appears when two hydrogen atoms approach one another. Each contains one proton and one electron. When the atoms are far apart, their electrons belong mostly to separate atomic states. As they draw closer, the electron wave functions overlap. Under suitable conditions, the electrons occupy a shared molecular state that lowers the total energy of the pair. Energy is released, and a hydrogen molecule forms. The bond does not resemble a rigid rod connecting two tiny balls. It is a stable distribution of electron probability spread across both nuclei. The nuclei remain separated because their positive charges repel at very short distance, while the shared electrons attract both nuclei. A balance appears at one preferred separation. If the atoms move farther apart, the bond weakens. If they are pushed too close, repulsion rises sharply. The molecule settles near the lowest available energy, just as the electron in an atom settles into a stable ground state. Other elements bond differently because their outer electron structures differ. Some atoms tend to lose electrons and become positively charged ions. Others tend to gain electrons and become negatively charged ions. Oppositely charged ions attract, producing ionic bonds. Common salt forms through this pattern when sodium gives up an outer electron and chlorine accepts it. The resulting ions arrange themselves into a repeating crystal lattice, held together by the collective electric attraction of the structure. In covalent bonds, atoms share electrons rather than transferring them completely. Carbon is especially important because it has 4 outer electrons available for bonding and can form stable connections with several neighbours. It bonds with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and with other carbon atoms. Carbon chains can be straight, branched, ring-shaped, or folded into intricate three-dimensional forms. This flexibility makes carbon central to the chemistry of life. Though carbon chemistry is not alive by itself, it becomes biologically significant when networks of reactions organize carbon compounds into systems capable of metabolism, replication, and evolution. Water demonstrates how molecular shape creates properties absent from the individual atoms. A water molecule contains 2 hydrogen atoms bonded to 1 oxygen atom. The arrangement is bent because electron pairs around the oxygen occupy space in a way that favours a particular geometry. Oxygen pulls shared electrons more strongly than hydrogen, giving one side of the molecule a slight negative character and the hydrogen side a slight positive character. Water is therefore polar. One molecule attracts another through relatively weak hydrogen bonds. Each bond is modest, but vast numbers of them act together. They give water an unusually high capacity to absorb heat, help create surface tension, raise its boiling point, and shape proteins and genetic material. Ice becomes less dense than liquid water because hydrogen bonds hold molecules in an open crystal arrangement. Ice therefore floats, insulating the liquid beneath it. An atomic pattern becomes a planetary and biological condition. Molecules also absorb and emit light in characteristic ways. Atoms possess electronic energy levels, while molecules add rotational and vibrational states. A molecule can turn, stretch, bend, and twist, but only certain changes in energy are allowed. These transitions interact with particular wavelengths of radiation. Water vapour, carbon dioxide, methane, and other gases absorb infrared light through their molecular motions, influencing planetary climates. Pigments absorb some colours and reflect others. Chlorophyll captures portions of visible light, helping biological systems store solar energy and chemical bonds. Spectroscopy reads these patterns from great distances. Light passing through a planetary atmosphere can reveal the molecules present there, while light from interstellar clouds exposes water, carbon monoxide, ammonia, and organic compounds. Chemistry leaves a signature in radiation long before any sample is touched. The same principles build solid worlds. In cooling disks around young stars, atoms and molecules collide, stick, fracture, melt, and recrystallize. Silicon and oxygen form strong frameworks that become silicate minerals, the main material of many rocky planets. Iron joins metallic cores, or combines with oxygen and sulfur, carbon enters gases, ices, minerals, and organic compounds. At low temperatures, water, methane, ammonia, and carbon dioxide freeze into grains that gather into larger bodies through gravity and repeated collisions. Planets inherit their compositions from local temperature, available elements, and the chemical history of the disk near a star. Volatile substances may evaporate, favouring rock and metal. Farther away, ices survive and contribute to giant planets and frozen moons. Atomic bonding therefore helps determine both what a planet contains and where different kinds of planets can form. Chemistry is shaped by environment because reactions must cross energy barriers. Two molecules may be capable of forming a lower energy product, but fail to react because their existing bonds must first be disturbed. Heat can provide the necessary energy. Light, electrical discharges, radiation, pressure, mineral surfaces, and catalysts can open other pathways. A catalyst speeds a reaction by providing an easier route without being consumed. In living cells, enzymes perform this role selectively. Their folded shapes hold reactants in favourable positions, weaken particular bonds, and guide products into new forms. The chemistry of life is therefore not a random churning of molecules. It is a controlled flow through networks of possible reactions, shaped by structures that have themselves arisen through evolution. Large biological molecules depend on weak as well as strong interactions. Covalent bonds preserve the main framework of proteins, nucleic acids, sugars, and lipids, hydrogen bonds, electric attractions, and subtle forces between nearby electron clouds determine how these molecules fold and recognize one another. A protein's function depends on its three-dimensional shape, which emerges from many local interactions acting together. A strand of genetic material stores information because its backbone is stable, while its paired bases connect through predictable patterns. Cell membranes form because certain molecules contain one region attracted to water and another that avoids it. In water, they arrange themselves into sheets and enclosed compartments without an external builder. The properties of atoms make self-assembly possible, and self-assembly allows chemistry to create boundaries, cycles, and organize systems. None of this means that life is an automatic consequence wherever atoms exist. Most atomic matter remains lifeless. Many planets are sterile, many molecules are simple, and many environments destroy complex structures faster than they form. The origin of life requires conditions still being investigated, including sources of energy, suitable solvents, catalytic surfaces, and pathways by which information and metabolism become linked. Yet atoms make these possibilities available. Their electron structures support both stability and change. Bonds can endure long enough to preserve form, but they can also break and rearrange under attainable conditions. If bonds were too weak, complex molecules would fall apart. If they were too strong, chemistry would freeze into unchanging structures. The useful middle ground allows matter to remember and transform. This balance explains why chemistry becomes the bridge between atomic simplicity and cosmic complexity. Nuclei determine which elements exist. Quantum mechanics organizes their electrons. Electron patterns create bonds. Bonds create molecules and solids. Molecules create atmospheres, oceans, minerals, and reaction networks. In a few environments, those networks become capable of maintaining themselves and passing information across generations. The universe does not need a separate set of building blocks for every new level. It repeatedly rearranges the same atoms, and each arrangement brings properties that no isolated atom possesses. Hydrogen and oxygen are gases under ordinary conditions, yet together they form liquid water. Carbon, hydrogen, oxygen, and nitrogen can become a scent, a pigment, a membrane, or a strand of genetic material. Iron atoms can form a crystal, enter a planet's core, or sit inside a protein that carries oxygen through blood. The identity of the atoms remains, while their collective behavior changes. Chemistry is the art permitted by quantum restriction. Because atoms cannot do everything, they can do particular things reliably. Because those particular things can be combined, the range of larger structures becomes almost without limit. Stable atoms provide the alphabet, but bonds provide grammar. From that grammar, matter forms worlds and, in rare places, systems able to preserve a history of their own. Atomic matter appears so dependable that its existence can seem inevitable. Protons endure, electrons remain light, nuclei hold together, and the periodic table unfolds in an orderly sequence. Yet this stability rests on relationships among particle masses, electric charges, quantum rules, and force strengths. None of these quantities can be changed independently without consequences. A small alteration in one part of the system can be softened by another change, while the same alteration made alone may erase whole classes of nuclei or prevent stars from producing useful elements. The question is therefore not simply whether the universe is balanced on one mathematical knife edge. It is whether the region of physical possibility that permits long-lived atoms, varied chemistry, and energy-producing stars is broad or narrow, and why the laws of nature place the observable universe within it. The simplest atom already depends on several compatible facts. The proton carries a positive charge whose magnitude matches the electron's negative charge. The proton is far heavier than the electron, allowing the electron cloud to extend well beyond the nucleus. Electromagnetism is strong enough to bind the pair, but quantum uncertainty prevents the electron from collapsing into an arbitrarily small region. The proton is stable for at least enormously long periods, and the electron is the lightest known charged particle, so it has no lighter charged state into which it can decay. If these relationships were radically different, hydrogen might not survive as a neutral atom. Hydrogen matters because it is the fuel from which stars begin. A universe without stable hydrogen would lose the main reservoir for long-lived stellar fusion. The relative masses of the proton, neutron, and electron are equally important. A neutron is slightly heavier than a proton. This allows a free neutron to decay through the weak interaction. While neutrons bound inside suitable nuclei can remain stable, the mass difference also helps protect ordinary hydrogen. A proton and electron do not spontaneously combine into a neutron because the neutron is heavier than their combined resting masses. Additional energy is required if the relationships were shifted enough. Electron capture by isolated protons could become energetically favorable, removing neutral hydrogen and filling the universe with neutrons or neutron-rich matter. A change in the other direction could alter neutron decay and the balance of protons and neutrons during the first minutes. The primordial abundance of helium would change, and the later supply of hydrogen available to stars would change with it. These masses emerge partly from deeper ingredients. Protons contain 2 up quarks and 1 down quark, while neutrons contain 1 up quark and 2 down quarks. The down quark is heavier than the up quark, contributing to the neutron's greater mass. Though electromagnetic effects and strong interaction energy also matter, altering quark masses changes the energy difference between protons and neutrons and can reshape nuclear stability. The consequences resist simple thresholds because nuclear energies and forces change together. Still, the broad sensitivity is real. If protons become unstable, ordinary atomic matter disappears. If neutrons cannot remain bound, nuclei heavier than hydrogen become difficult or impossible. If both remain stable in very different proportions, the universe may leave its first minutes with a radically altered mixture of elements. The strong interaction introduces another layer of balance. It confines quarks inside protons and neutrons, and its residual effect binds those particles inside nuclei. If nuclear attraction were much weaker, deuterium could fail to remain stable. Deuterium is the gateway through which both primordial nucleosynthesis and much stellar fusion proceed. Without it, helium production in the early universe is suppressed, and stars face a broken reaction pathway. If nuclear attraction were stronger, new bound states could appear. Two protons might bind more easily, and nuclear reactions inside stars could proceed at different rates. Exact outcomes depend on how reaction rates, stellar structures, and particle properties change together. The secure conclusion is quieter. Nuclear physics occupies a region that supports both stable hydrogen and a useful range of heavier nuclei, and moving far from that region can impoverish or erase chemistry. Electromagnetism must also remain in workable proportion to the strong interaction. Inside a nucleus, the strong force attracts nearby protons and neutrons, while electric repulsion pushes protons apart. For light nuclei, attraction wins comfortably. As nuclei grow, repulsion accumulates across the whole structure, while the strong force remains short-ranged. This competition limits the size and stability of elements. If electromagnetism were stronger relative to the nuclear force, large nuclei would become harder to bind, reducing the supply of elements such as carbon, oxygen, silicon, and iron. If it were weaker, very heavy nuclei might be easier to form, but stellar reactions, atomic sizes, and chemical bond energies would also shift. The pattern of stable isotopes, radioactive decays, and stellar production routes could be transformed. Stars add further conditions. They must be able to ignite nuclear fusion without exhausting their fuel almost immediately. Gravity compresses stellar gas, while thermal pressure resists collapse. Fusion releases energy and helps maintain the balance. If gravity were far stronger relative to particle physics, stars could be smaller, hotter, and shorter-lived. If far weaker, gas clouds might require much greater mass to ignite or might struggle to form stars efficiently. Stellar lifespans depend on gravity, electromagnetism, nuclear reaction rates, and particle masses together. Long-lived stars matter because complex chemistry needs time. Heavy elements must be forged, dispersed, and gathered into systems where slow processes can unfold. A universe that forms atoms but only brief, unstable stars may possess chemistry without providing many enduring environments in which complexity can accumulate. Carbon is often placed at the center of fine balance discussions because stars produce it through a sequence involving 3 helium nuclei. An excited state in the carbon nucleus increases the efficiency of this process under stellar conditions. A related nuclear state helps control how readily carbon captures another helium nucleus to become oxygen. Changes to nuclear forces can shift these energy levels and alter the amounts of carbon and oxygen made by stars. Early arguments sometimes describe this as an extraordinarily precise coincidence, while later calculations show that some variation may still leave substantial quantities of both elements. Sensitivity should not be exaggerated. The allowed region may be wider than a single narrow point, and unfamiliar chemistry may support possibilities not yet known. Yet the existence of a tolerable range does not remove the underlying question. The laws still select one set of values from many mathematically conceivable sets, and that set permits stable nuclei, luminous stars, complex molecules, and observers made from them. Physics can describe much of this dependence, but interpretation begins where tested explanation ends. One possibility is that the constants could not truly have been otherwise. A deeper theory may eventually show that their values follow necessarily from a more fundamental structure. What looks adjustable may be fixed by hidden consistency. Another possibility is environmental selection across a larger collection of regions or universes with different effective properties. In that case, observers naturally arise only where atoms and complexity are possible, so any observed universe is filtered by the conditions required for observation. This restrained anthropic idea does not imply design. It states only that observations arise from places compatible with observers. A third possibility is that the values are simply contingent, neither forced nor selected, and the apparent balance is a fact without a deeper accessible explanation. Deliberate creation appears in philosophy and theology, but current physics cannot test it like a particle interaction or cosmological model. The evidence does not choose cleanly among these wider interpretations. Fine-tuning arguments become strongest when they identify clear physical dependencies, and weakest when they assign precise probabilities without a justified distribution of possible laws. There is no known cosmic control panel selecting constants randomly. Without knowing which values are possible or how they should be weighted, numerical odds create false precision. What remains scientifically meaningful is the map of consequences change this relation, and hydrogen shifts, change another, and nuclei fail, move elsewhere, and stars alter their lives. Atomic existence occupies a structured region in the landscape of physical law. Whether that region is rare, necessary, selected, or accidental remains unresolved. The universe therefore does not answer the question of atoms merely by showing how they form. It also reveals that formation depends on a network of compatible conditions. Atoms are robust once those conditions are present, but the conditions themselves invite a deeper mystery. Matter holds together because forces oppose and complement one another. Masses permit some transformations and forbid others, and quantum states create stable floors beneath which electrons cannot fall. The balance is not a fragile ornament trembling at every disturbance, yet neither is it guaranteed by anything currently known. It is durable order resting on foundations whose final explanation remains out of view. The atoms that form a thinking brain do not begin in the brain, or even on the planet that carries it. Their history reaches backward through stars, interstellar clouds, ancient explosions, and the first minutes of the universe. Hydrogen nuclei emerge during primordial nucleosynthesis. Electrons remain free until the cosmos cools enough for atoms to form. Gravity gathers those atoms into the earlier stars, where fusion begins the long manufacture of heavier elements: carbon, oxygen, nitrogen, silicon, phosphorus, sulfur, iron, and many others are forged through stellar burning and violent stellar death. They are scattered into space, mixed into new clouds, and drawn into later generations of stars and planets. Matter that once drifts in darkness becomes rock, ocean, atmosphere, and living tissue. Eventually, some of it enters a nervous system capable of memory, prediction, and curiosity. The universe does not merely contain atoms. Through cosmic history, atoms become arranged into structures that can ask why atoms exist at all. This return of matter upon its own origins is not required by the basic definition of an atom. A carbon atom does not contain an instruction to become part of a cell. An oxygen atom does not anticipate oceans or lungs. The possibility appears only through organization. Atoms form molecules. Molecules form reaction networks. Some networks become enclosed, self-maintaining, and capable of copying information with variation. Natural selection then preserves arrangements that survive and reproduce more effectively. Over immense spans of biological time, nervous systems grow more elaborate. Signals travel through membranes. Cells specialize. Brains form internal models of the world, compare present conditions with memory, and adjust behavior toward possible futures. Conscious experience remains a deep unsolved problem, but its material dependence is clear: injury, chemistry, sleep, disease, and electrical activity all alter thought because thought is linked to organized physical processes in the brain. The atoms are not individually conscious. The pattern they form supports a level of behavior that no isolated component displays. This is another form of emergence, like chemistry arising from electron structure or solidity arising from exclusion rules. The larger property is real, yet it belongs to the organization rather than to any single part. A brain contains atoms older than the planet beneath it. Its hydrogen descends largely from the early universe, while its carbon, oxygen, iron, and phosphorus are forged in stars. Sodium and potassium ions cross cell membranes, helping create the pulses that carry information. Thought therefore depends on elements with separate cosmic histories, brought together through geology and evolution. Yet no atom remains permanently assigned to one body. Matter is exchanged continuously with air, water, food, and soil. Identity rests in an evolving pattern that persists while its material components flow through it. This makes the relationship between atoms and observers more subtle. The observer is made from atoms, but is not merely their sum. The order among them matters. The timing of their interactions matters. The history encoded in their structure matters. The same elements arranged differently may become bone, blood, bark, ocean, ash, or stone. Physics permits the possibilities. Chemistry selects stable combinations. Biology preserves functioning systems, and evolution explores forms over time. No boundary between these levels is absolute, but each level introduces useful descriptions that cannot be replaced easily by listing every particle. A complete account of the brain in terms of quarks and electrons would be overwhelmingly detailed and would still fail to explain thought in a practical way. Higher patterns require their own concepts, such as cells, circuits, learning, and memory. The atomic foundation remains essential, but foundations do not exhaust the architecture built upon them. Looking inward, matter encounters the same strangeness found at the beginning of cosmic history. The atoms in a brain are mostly empty in the classical sense. Their electrons occupy probability distributions rather than clear paths. Their nuclei contain quarks and gluons in continual quantum activity. Their mass comes largely from confined energy. The apparently solid organ that produces a thought is therefore built from structures that resist ordinary visualization. Stability emerges from uncertainty. Solidity emerges from fields. Memory emerges from changing electrical and chemical states. The world appears continuous at human scale because immense numbers of quantum events combine into reliable patterns. The unfamiliar rules of the small do not make ordinary reality unreal. They make ordinary reality possible. Every calm surface and lasting object is a large-scale expression of deeper processes that remain in motion. The question of why everything familiar is made of atoms therefore turns into several questions at once. It asks why the universe contains particles with the right charges and masses. It asks why the strong force creates stable protons and nuclei. It asks why quantum mechanics provides electron states that do not collapse. It asks why cosmic expansion cools matter through the sequence required for binding. It asks why stars can forge a diverse set of elements, and why chemistry can assemble those elements into structures of growing complexity. Physics answers many parts of this chain with impressive precision. Experiments reveal particle interactions. Telescopes detect ancient radiation. Spectra identify elements across distant galaxies. Nuclear models explain stellar burning. Quantum theory predicts atomic behavior, yet the deepest layer remains open. The laws describe how atoms form given the structure of nature, but they do not yet explain why that structure is the one realized. A deeper theory may reveal that the known particles and forces emerge from something more fundamental. The apparent variety of fields may turn out to be different expressions of one underlying framework. Space and time themselves may be emergent rather than basic. Current research explores such possibilities, but no confirmed final account exists. Atoms may someday be understood as inevitable consequences of a deeper order, or they may remain one stable possibility among many. The absence of a final answer does not weaken the achievements already made. It marks the boundary between explanation and origin. Science often advances by turning familiar things into questions. Falling objects become evidence about gravity. Starlight becomes evidence about distant matter. Atomic spectra become evidence about quantized energy. The ordinary fact that matter consists of atoms becomes a doorway into the early universe. Particle physics, chemistry, stellar evolution, and the conditions for complexity. Each answer removes one kind of mystery and reveals another beneath it. The atom is explained as a bound quantum state, but the values that permit that state remain to be explained. The proton is described through quarks and gluons, but confinement still resists simple intuition. The cosmic microwave background confirms a hot early universe, but the origin of its initial conditions remains uncertain. The growth of life follows chemistry and evolution, but conscious experience remains incomplete. Knowledge expands not by closing every opening, but by making the openings clearer. At the end of the chain, atoms become instruments for studying atoms. Carefully controlled matter forms clocks, detectors, computers, telescopes, and particle accelerators. These devices measure atomic transitions, probe protons, detect ancient photons, and read the composition of stars. Brains interpret the results and build descriptions of processes far beyond direct experience. The same laws under investigation also make the investigation possible. Electrons produce signals, store data, and participate in understanding them. The mystery turns inward because the observer and the observed share the same material foundation. There is no view from outside the universe, and no investigator made from a separate substance. Matter studies matter from within. This circularity does not make knowledge impossible. It gives knowledge its remarkable character. A small region of the cosmos can reconstruct events from billions of years before its formation. Atoms created in ancient stars can determine the ages of those stars, map the expansion of space, and infer conditions before any atom exists. The universe becomes locally aware of its own history not as a single cosmic mind, but through temporary living arrangements of matter. Those arrangements are fragile. They depend on stable environments, flowing energy, inherited information, and a narrow period in planetary history. Yet while they endure, they extend the story of atoms beyond structure and chemistry into reflection. The original question remains open at its deepest level. Everything familiar is made of atoms because the universe cools into conditions where atoms are stable, because its particles and forces permit them, and because atoms provide durable units from which complex structures can grow. But why the laws possess that form, why the constants occupy their measured values, and whether other forms of matter and complexity are possible elsewhere remain unresolved. The answer ends not with certainty, but with a view of matter carrying its own history. Hydrogen from the early universe, carbon from stars. An electron shaped by quantum law gather briefly into a pattern that looks back across cosmic time. In that pattern, atoms become more than the building blocks of the visible world. They become the means by which the visible world begins to understand how it came to be.